test is next week. But those lab tests are fun. That's what. It never ends. I heard you guys complaining about it all over there. Oh yeah. So lab exam 2 is next week. And remember that it's cumulative, so you need to go back and look at the old stuff. Everything's cumulative. I can't change it now, it's in the syllabus. No. No, I can't. I mean, I'm allowed to, but like morally, I feel like I can't. So it's cumulative. Okay. All I want is for you to remember everything I say from now on. Okay? Is that so much to ask? Yes. Each thing that I say, I want you to hear it, remember it forever. Okay? Yeah. It's on video. It's on. Just remember what I say forever. That's all. What? Yeah, but I wanted in video in your brain. Brain video. Okay. So there's no class on Thursday, so we have to get far enough that you can have some problems to work on. Yes. No, it's a good one for getting ready for the lab test because it's no new stuff. It's just old, like practicing like the stuff from the last 3 labs or so. So it'll be helpful. Okay, so what are we talking about? We started talking about, so we did free body diagrams. And then we had to talk about the directions that forces are applied, like different types of contact forces, what directions do they act? And we did one example with pushing, right? We started talking about, we haven't? Does it say? Oh, that's all. Okay. So we finished with free body diagrams? Okay. Oh, good. I mean, I'm glad I know that instead of starting in the middle of, okay. So, with free body diagrams, we had to know the direction of forces that are applied. And so now we're going to go through the 3 types of contact forces. I'm not used to hearing that in class. That's okay. That happens. That's what babies do. Actually, if that's what all babies do, you got a good baby. Yeah. 3 types of contact forces. The first one is a pushing contact along a flat surface. The second one is a pulling contact. And we're always going to think of pulling contacts as involving cables. So anytime you pull on something, you could imagine that you're pulling on a little piece of cable that's pulling on the thing, and that's sort of how we're going to think about it. So cables. And then the last one is friction. So the first type that we're going to deal with is pushing contact along a flat surface. So when two objects push against each other, the force is always perpendicular to the surface of contact. And toward the chosen body, away from the contacting body. Okay, so here's the type of contact we're talking about. Let's imagine that we have these two carts that are in contact. I'll call this one cart 1, the one on the left, and this one cart 2. And let's say that there's a force applied here. So first of all, where is there pushing contact happening in this problem? There's a pushing contact between the wheels and the ground. You know, and actually, to think about when something is pushing or pulling, think about whether the force is preventing the two objects from like moving through each other. That's anytime that's the case, it's pushing. So like think about the force that the floor is applying to this table. If the force that floor, like imagine the floor suddenly turns to tissue paper and it can't apply that force anymore. Okay? The table would go right into the floor. And that's how you know that this is a pushing contact that the floor is applying to the table. Okay. So that's what's going on between the wheels and the ground here. So that's a pushing contact. That's what's going on here between these wheels and the ground. So that's a pushing contact. And that's what's happening where the two bodies are in contact with each other. So that's a pushing contact. Okay. So let's think about a free body diagram for each one of these. Okay, so free body diagram, we'll do it first for part 1. So draw a closed outline. And then what forces are acting on this body? There's a weight force. I'll call it M1G. There's a force being applied to this by the ground. So now we have to think about the rules of pushing contact. Okay, so what's the surface of contact? We know it's perpendicular to the surface of contact. So what is the surface of contact between the wheels and the ground? That would be like the ground. Okay. And so we know it's perpendicular to that. So it's up or down. Okay. And now we have to think about, is it up or is it down? Well, it's toward what we're choosing to isolate, away from the contacting body. So it's toward the part away from the ground. So it's up. Okay. I mean, you could also just think of it as like, if it pushed a little harder, what direction would the thing go? You know what I mean? you'd rather think about it that way. Like if the ground all of a sudden pushed a little harder, it would make this go up, and so the force is up. Okay, so there's an upward force like this. I'll call it N1. So that's just a variable name. You can call it whatever you want. I'm going to call it capital N pretty often because that's what people often use. It stands for normal. That type of force is called a normal force. But if you wanted to call it Q or Z or M, it's just a variable name. And now let's keep going around the boundary and look for places where other things are touching the boundary. The next place we get to is over here. This is where the boundary is contacted by the cart 2. That's a pushing contact. So it's perpendicular to the surface of contact, and then it's toward the chosen body. So I'll call that F. No, we already have an F there. I'll call that F2. And then keep going around the boundary, and the last time that anything makes contact with the body is just this force over here. We don't even have to know what it is producing that force. We'll just put that F in like this. Any questions about that? The what? It doesn't matter here because when you choose something to isolate, all you care about after you apply the weight is what's happening right at the boundary. And so now we're going to isolate cart 2. And the thing that's a little surprising to most people is the free body diagram here won't have this in it. This doesn't see this force, because it's not applied to the boundary of 2. So yeah, just be really disciplined about thinking the gravity force is applied, and then you're just going around the boundary of your chosen object. What's making contact with that boundary? What do you guys think is the most exciting part of this so far? I didn't. That was like 2 weeks ago. Oh, in lab. Yeah, that is good. The girl in lab. Oh, that was good. Yeah. I was hoping you were going to say something about pushing contacts, but thank you. I've done a lot of these, so that probably makes it easier for me. Now let's do a free body diagram of cart 2. Okay, so there's the weight force. I'll write that as M2G. We don't know what that mass is. And I'll start at the wheels and then work around the boundary counterclockwise again. So at the wheels, there's a pushing contact from the ground. That's also up toward the chosen body. I'll call that N2. There is nothing happening over here, nothing happening on top. And then when we get over here, there's a force applied to cart 2 by cart 1. So there's a force like that. I'll call it F3. And then those are complete free body diagrams. Later on, we're going to learn that actually this force that's applied to this one by this one is always exactly the same magnitude as the force applied to this one by this one. So that'll be a useful thing, but for now we don't need to think about that. But these are complete free body diagrams. Okay, so let's do one like that, but actually do calculations. So let's say we have one cart here that has a mass of 10 kilograms and one that has a mass of 20 kilograms. You'll like this. Babies never think they're going to like physics problems, but then they get so into them. Yeah. She's going to like the calculations even more. Exactly. Okay, so let's figure out, let's say we want to know what's the force applied, on the 20 kilogram cart by the 10 kilogram cart. It doesn't take too much, creativity or whatever to think of how a calculation like this would be useful in an engineering application. If you have part of a machine or something and you want to figure out how thick of metal or what type of metal you have to use in this wall of this piece of the machine so that it doesn't break under the kinds of motions that it's going to deal with. These are the kind of calculations you do in mechanical engineering all the time. Okay, so the first step is, what we're going to do is draw free body diagrams. Well, we'll start with one free body diagram and then we'll use Newton's second law. The thing is, we don't know yet what the acceleration is, and you can imagine, this force is going to make those two things accelerate. So the first thing we're going to do is isolate all of this like it's a single unit and calculate what the acceleration is. So we're going to isolate both together, and we're going to do that so we can calculate the acceleration. Once we find the acceleration of the two together, then that's the same acceleration as either one individually, so we can use what we found in the first step. Okay, so free body diagram of both of them together. So there's the outline. What forces are acting? What's the first one? Gravity. And the magnitude of that force is the mass times 9.81. What's the mass of this chosen object? 30, yep. Both of those two added up. So 30 times 9.81 is 294.3. And then there's an upward force on the wheels. I'm going to call that, so with these normal forces, I'm later going to isolate just one of these individually. So instead of just calling this N, I'm going to call this N total. We don't get confused about thinking the different N's are all the same. So N, the subscript TOT, total. And now go around the boundary. The next place that something from the outside is contacting the boundary is where that force is applied. So that 30 Newton force acts on the right side. Keep going around the boundary. Now, these two apply forces to each other, but that's not a thing if we're isolating them both together. We don't care about what happens inside the boundary, okay? What happens inside the boundary stays inside the boundary. This is like a free body diagram of Las Vegas. So keep going around. Don't worry about that. Just follow the boundary. You get here, nothing. You get back to where you started. And so now we know we're done. That is equal to 30 times 9.81. So Newton's second law says, all right, so now we have to take the step of going from, we have these arrows drawn, but we have to represent those as vector components. So if we have a vector with a magnitude of 294.3 pointing down, what would be the vector components? 0 for x, and then negative 294.3 because it's in the negative y direction. You could also, if that doesn't pop right into your head, think of a coordinate system like this. Here's the x-axis. You go 270 degrees there. So it would be 294.3 times cosine and sine of 270, and it'll give you that same answer. Okay, so the first force is 0, negative 294.3. What about this one that has a magnitude of n total, and it's acting straight up? Exactly, 0, and then positive n total because it's in the positive y direction. And what about that 30 that's pointing in the negative x direction? Yep, negative 30, 0. And the last thing we have to do is we have to think about if there's anything we know about the acceleration. And in these kind of problems, there always is one thing we know. Before we do any calculations, we can see from the way the problem's designed that any acceleration is going to be in the x direction only. I mean, we can actually even see that it's going to be negative x, but we don't have to worry about that. All we need is, we need to know that the y component of acceleration is 0. Okay, so I'm going to just write that acceleration as a variable a in the x position. The x component is a, the y component is 0. So Newton's second law says, add up those three forces, and those are equal to the mass, which is 30 kilograms, times the acceleration, which we say is a0. Any questions about setting up Newton's second law yet? Okay, so Newton's second law gives an x equation and a y equation. The x equation says 0 plus 0 minus 30 is equal to 30a. And the y equation says negative 294.3 plus n total plus 0 is equal to 0. What we want to know is the acceleration. So, bless you. We want to know the acceleration. So this is the equation that we care about. The other one would let us calculate that normal force, but the problem doesn't ask for that. So that x equation says negative 30 is equal to 30a, or a is equal to 1 meter per second squared. Negative 1, sorry. So we know that that variable a is negative 1. What we really want is the acceleration vector. So how do we go from that value of negative 1 to the acceleration vector? Well, what you're going to do for the acceleration here, and you're going to do it for when you want force vectors later, is you already have all this stuff represented in Newton's second law. Like, we know that this force applied by the ground is this. We just don't know what n total is yet. And we know the acceleration is a0. We just don't know what a is yet. So once you calculate a, just take this value and plug it back into this vector. And so after you plug it back in, you get that the a vector is equal to -1, 0. So now we know the acceleration. And now that we have that, we can isolate one of those carts individually to figure out the force that's applied to it by the other one. We're trying to figure out the force that's applied to the 20 kilogram by the 10 kilogram. So I'm going to isolate the 20 kilogram cart. So here's a free body diagram of the 20 kilogram. There's a weight force that's equal to 20 times, yes? We found the acceleration of both of those two carts together, but since they're, if one moves, the other one moves. So now that we found the acceleration of both of those two together, we can use that acceleration now in Newton's second law for just the cart that we want. That's why that was our first step. Otherwise, we'd have one equation for two variables, and we wouldn't be able to solve for anything. Okay, so the weight is 20 times 9.81, so 196.2. And then there's an upward force from the ground. I'll call that N2 or N20. And keep going around the boundary. And when you get over here, that's where that 30 Newton force is. So over here is a 30 Newton force. There's nothing applied to the top. And then when you get over here, there's a pushing contact from the 10 kilogram cart. So I'll write this as a pushing force. I'll just call it F. And now Newton's second law. So the weight force is 0, negative 196.2. The normal force, that's in the positive y direction. So that's 0, positive N20. The 30 Newton force is in the negative x direction. So that's negative 30, 0. And then the F is acting in the positive x direction, so that's positive F, 0. That's all the forces. And the sum of all those forces has to be equal to the mass of the object we're isolating. What's the mass of the object we're isolating this time? 20. Times the acceleration vector that we figured out in step 1. So negative 1, 0. So this gives us an x equation and a y equation. The x equation says 0 plus 0 minus 30 plus f is equal to negative 20. And the y equation says negative 196.2 plus n20 plus 0 is equal to 0. Okay, so what we're trying to find is the force vector. We're trying to figure out what this force vector is. Okay, that's this one here, F0. And we'll know what that force vector is as soon as we know what F, that variable F is to plug in there. We only care about the equation that's going to let us calculate F. The other one, you know, if we were trying to find that normal force N20, you know, then that would be useful, but we just don't happen to be trying to find that. So this is the one we want. So this equation says negative 30 plus F is equal to negative 20. And so F is equal to 10 newtons. And now to express that as a force vector, well, there's sort of two ways to think about it. First, we already drew what direction it's pointing. So you can think of that vector as going in that direction with a magnitude of 10. So 10 newtons going that way. Or you can also plug that variable back into the vector components. We already expressed this force vector as F0. So it has to be this. Nope. Yeah, you don't have to do that. Okay, so now let's figure out what's the force on the 10 kilogram cart by the 20 kilogram cart. Let me go back to the original picture. Okay, so what we know is that the force, this one applies to this one, is 10 newtons going that way. Okay. It turns out that one of the big equations we're going to study, one of the big laws that we're going to study in a little while, says that if this is applying a force of 10 newtons that way, this has to be applying a force to that one of 10 this way. Okay. So that's a fact that we'll spend a lot of time on. But for now, we're gonna now isolate the 10 kilogram cart and do that calculation and see that it works out. Okay, that's how it works out. So now we want to figure out the force on this one by this one. And what we should find out is that that 10 kilogram cart has a contact force of 10 newtons pushing this way. Okay. So now which cart are we going to isolate? Yep. So Freebody diagram of the 10 kilogram. There's a weight force. This time what we're isolating has a mass of 10 kilograms, so the force is 98.1, weight force. And then starting at the wheels, there's a pushing contact that I'll call N10. Okay, and so the 20 kilogram cart's over here, right? And the 30 Newton force is over here applied to this one that's not drawn there. So, but now we're just going around the boundary. We get over here. So this is the contact force applied by the other cart. Okay, it's a pushing contact, so it has to be toward this body. I'll call this capital R for reaction force. Doesn't, that's just a variable that we're going to solve for. What about the 30 Newton force? That doesn't go there because that's acting on something else. That does not apply to this boundary, so we just skip it. And up here, nothing over there, right, if I remember the problem. So this is it. This is a complete free body diagram for the 10 kilogram body. Only those three forces are acting on it. So Newton's second law says 0, negative 98.1 plus 0, positive N10 plus that R is pointing in the negative X direction, so negative R 0 is equal to the mass, 10, times the acceleration. Do we know the acceleration vector? Yep, that's still the same as both of them together or the second one by itself, so that's negative 1, 0. That's what we did in the first step. So this gives an x equation and a y equation. The x equation says 0 plus 0 minus r is equal to negative 10. And the y equation says negative 98.1 plus n10 plus 0 is equal to 0. We only care about getting that r value, so this is the one that's useful to us. And so the x equation says 0 just says negative r is equal to negative 10. So r is equal to 10. Okay, so now you have to be careful. We figured out what the variable value is, but we need to make sure that we put it into the force vector the right way. The easiest way to visualize it is we know that it's pointing this direction. We know the magnitude's 10, so that force vector just has to be 10 newtons like that. Or you can also take that variable value, plug it into the components of the force vector that we know, take 10, plug it into this, and you get a force vector of, this time, negative 10, 0 newtons. So that's kind of cool how that works out. We isolated cart 2, and it had the 30 Newton force on it, and we calculated that contact force between them was 10 newtons. Then we isolated cart 1. It didn't even have that contact force, that 30 Newton force in it, but somehow it all works out so that you can see that contact force has the same magnitude either way. And all that changes is the direction depending on which body you're looking at. Any questions about that? Yeah, that's so really those wheels, when I draw those wheels, it's mainly meant as a shorthand way to say that there's no friction in this problem. And I could also just have drawn the boxes on the ground and just written no friction or something. But that's what those wheels are supposed to mean, no friction. Okay. Let's do one more. So let's say this one's in an elevator, and there's a 1 kilogram box with a 2 kilogram box sitting on top of it. And let's say that the elevator has an acceleration down of 3 meters per second squared. What's the force applied to the, let's see, top box by the bottom box? Okay, in the last problem, the first step was isolating both of the two things together to figure out their acceleration. This time we can skip that because we already know the acceleration is 3 meters per second squared down. So this time I'll just start by isolating the 2 kilogram box. The weight force is 2 times 9.81. And then there's a pushing contact applied to this one by the one under it. It's coming toward the chosen body, away from the contacting body, so it has to be up. So I'll call that N. And then Newton's second law, we have the weight force, 0, negative 19.62. And the normal force is in the positive y direction, so 0 N. And those are all the forces acting. And then those are equal to the mass of the chosen body, 2 kilograms, times the acceleration of that box, which is 3 meters per second squared down. So what would that be as a force, as an acceleration vector? Yeah, 0, negative 3. Any questions about that? Okay, so the x equation says 0 plus 0 equals 0. That's helpful. It's a good reminder. Doesn't let us solve anything though. And the y equation says negative 19.62 plus n is equal to negative 6. So this is the one that's useful this time. So negative 19.62 plus n is equal to negative 6. So n is equal to positive 13.62. newtons. Oh, by the way, just to avoid confusion on this, I'm always, whenever I'm using this capital N as a variable, I'm always giving it the fancy 2's and half. And then when I use it as newtons, it's just plain. Okay. So you can always tell in my notes which one, whether that's a variable or a unit. Okay, so the force vector applied to the 2 kilogram box by the 1 kilogram box has a magnitude of 13.62. Is it directed up or down? Up, because we knew it was up here. And so to write that as a force vector, you can write 13.62 newtons like that. Or you can take that value, plug it back into the force vector that we have in Newton's second law, and you get 0, positive 13.62. Yeah, I know. Okay, so going back to this original picture, so we know that the force on the 2 kilogram by this one is up at 13.62. So what do you think the force vector is on the 1 by the 2? Same magnitude, opposite direction. So down at 13.60. Yep. Okay, the second type of contact force that we're going to deal with is pulling forces. And like I said, we can always, even if there's no cable in the problem, we can always assume that there's a cable. So that's sort of how I'm going to think about that as we go through problems. So a cable always applies a force to a connected object that's parallel to the cable and it's away from the chosen object. So for example, if you have so let's say this is a pulley attached to the ceiling, and on one side you have let's call this little one mass 1, and this bigger one is mass 2. Then a free body diagram of mass 1 looks like this. You have the weight force of m1g, and the force applied by that cable is parallel to the cable, so it's vertical. And it's away from the chosen object, so it has to be up. And I'll write that. The variable I'll associate that, I'll call it T1, T for tension. And then free body diagram for box 2. So that is the weight of M2G acting down. And for this one, what direction is that cable force? I said that like a trick question. That was by accident, though. Because it's the same, you know. It's parallel to the cable, you know, so it has to be vertical. And it's away from the chosen body, which is this one, so it has to be. And here's a important thing that we're going to use all the time. Not like all that other stuff I say that you can just ignore. No, that was a joke. You even heard me because they were ignoring me already. You're like, we know. So if the cable only touches pulleys between its endpoints, class gets long, I know. So if the cable only touches pulleys between the endpoints, then the magnitude of the force it applies is the same everywhere. Only the direction changes. Okay, so let me do an example. So let's say you just have a box hanging from the ceiling. So there's a cable connected to the ceiling, and that's connected to this mass. Let's say this has a mass of 2 kilograms. And we want to know what's the force applied to the ceiling by the cable. So the first question is, between its endpoints, does this cable touch anything besides pulleys? It doesn't even touch any pulleys. So we know that the magnitude of the force that cable applies to the hanging mass is going to be the same as the magnitude of the force applied to the ceiling. Just the directions might be different, that's all. Okay? So first I'm going to isolate the 2 kilogram mass. There's the downward force of the weight, so that's 2 times 9.81, so 19.62. And then the cable force is parallel to the cable, away from the box. So is it up or down? Up. So I'll label that capital T for tension. And then write Newton's second law. So we have 0, negative 19.62 for the weight. And for the cable force, we have 0, positive T. And that's equal to mass, 2, times the acceleration of that box. That box is just hanging there. It's not moving, so the acceleration is 0. So the x equation says 0 plus 0 equals 0. That doesn't help. The y equation says negative 19.62 plus t is equal to 0. So this is the useful one. And it tells us that t is equal to positive 19.62. So the force that the cable applies to that box, is it 19.62 up or down or left or right or what? It's up. And we know that because we already drew it in the Freebody diagram. So the force vector you can think of like this. Or you can plug that value for t into the force vector from Newton's second law, and that gives you 0, 19.62. And those, agree that that force is up. But that's not what we're looking for. What we're looking for is the force vector that cable applies to the ceiling. Okay, so we know that the magnitude is the same. Because that cable doesn't touch anything between its endpoints other than pulleys. So the force applied to the ceiling has a magnitude of 19.62. What's the direction? Yeah, it's downward. So because if you think of the ceiling, we know that the force applied to the ceiling is parallel to the cable, so up or down. And this time it's away from the ceiling, so it has to be this way. So the force vector is 19.62 newtons down, or that in components is 0, negative 19.62. So that isn't really that surprising. I mean, if the cable's attached to the ceiling and you put too much weight on it, it pulls out of the ceiling. So you sort of have this feeling that the force is applied downwards, right? And you sort of have this idea that the force applied to the ceiling would be equal to the weight of the thing. If you make the weight too big, the cable will break out of the ceiling. But that's only the case if there's no acceleration. So now, what would the force be? So what force would the cable apply to the box So imagine this ceiling being on an elevator that's accelerating upwards. With an upward acceleration of, let's say, 2 meters per second squared. What is it? If the ceiling is an elevator, it's the ceiling. I don't know. This, that's what I meant to write, but it doesn't really make any sense. But the idea is just that that's the ceiling of an elevator, and that's the acceleration of the elevator. Okay, so now let's do the same thing, free body diagram of the box. So we have a weight force of 19.62 again. And the force applied by the cable is still up and has a value of T. But now Newton's second law is going to look different because of that acceleration. The left side will look just the same. The forces are still 0, negative 19.62, plus 0, positive T. And those are equal to a mass of 2 times an upward acceleration of 2 meters per second squared. So the acceleration is 0, positive 2. The x equation says 0 equals 0. The y equation says negative 19.62 plus t is equal to 4. And so t is equal to positive 23.62 newtons. So it's an upward force of 23.62 newtons, or if you plug that value into the vector, it's components of 0, positive 23.62. So having that elevator accelerate upwards makes that cable tension bigger. It puts a bigger requirement on the strength of the cable, bigger requirement on the strength of the ceiling, that kind of stuff. Any questions about that? So let me just do one quick thing where I just show, I'm going to do a real simple example that has a pulley in it, so you'll see how that works. And then we'll get out of here. Okay, so let's say that so there's a pulley here on this corner, on this ledge, and a cable goes over the pulley. And then on the other side, it's holding up, that cable's holding up a 5 kilogram box. And we want to know what's the force applied to the wall by the cable. Well, between the ends of this cable, all it touches are pulleys, so that's fine. We know the magnitude's going to be the same everywhere. So a free body diagram of the 5 kilogram box. We have the weight of 5 times 9.81, so 49.05. The direction of the force that that cable applies has to be parallel to the cable where it leaves this object. So it has to be like this direction, and it has to be away from the body. So it's an upward force. I'll call it T. And then Newton's second law says 0, negative 49.05 plus 0t is equal to 5 times, this thing's just hanging there, no acceleration, so acceleration vector is 0, 0. So the x equation says 0 equals 0. The y equation says negative 49.05 plus t is equal to 0. And so from the y equation, we get that t is equal to 49.05. Okay, so now let's think about the direction. That's the magnitude of the force anywhere along the cable. Let's think about the direction of the force that's applied to the wall. So at the wall, the force has to be parallel to the cable where it leaves the wall, so it has to be horizontal. So close to done. You almost made it. And then it has to be away from the wall. So this way, with a magnitude of 49.05. So it's a vector like this, 49.05 newtons. Or that's in the positive x direction. So 49.05, 0. Any questions about that? Okay, see you later.